Right. Now, in relation to this distribution function, I have another extra comment, and which is here. I want to comment further on the special case when the function f here in this relation, function f in this relation, or function f in fact in this relation, is replaced with the function absolute value of f to the power of p, where p is some positive number. Well, if you directly apply this identity, you will have something like this, obviously. It will be the n tilde distribution function of absolute value of f to the power of p, but what I claim is, in fact, that this can be further improved down to expression like that, x to the power p with the original distribution function, so the distribution function of the function f rather than absolute value of f to the power p. The reason for this is transfer of measure theorem, and I have to quickly recall that for you. Remember, in one of my earlier comments, we discussed with you the transfer of measure, and the setting there was something like this. We had a function which mapped some universal set x1. I will change notations a little bit to fit into this slide better, but if you trace down the changes, you will realize it's identical to the transfer of measure theorem as stated earlier. So we have some universal set, which this time I call x1, which is mapped by some function g into a measure space with a sigma algebra and a measure m. And we found with you a way how to transfer the measure structure from this codomain into the domain. And symbolically, I can say it like this. We can find a sigma algebra here, which will be sort of a pre-image of the sigma algebra here. And we can find a measure m1 here, which will be again a pre-image of the measure here, such that here we will have the Lebesgue measure space. Now, this theorem, or it's a symbolic representation for that theorem, it now will have one extra clause, which also connects the Lebesgue integration in this measure space, original measure space, and Lebesgue integration in this constructed measure space, and that's the connection. It says that the function f is Lebesgue integrable here if and only if the composition of f and g is Lebesgue integrable here, and the integrals in fact connected like that. Now, if you believe in this extra clause, I strongly encourage you to try to prove it. But if you believe in this extra clause, and if you let me take the function g like that, the function g which maps r plus into r plus like this, then under this mapping, the measure gn tilde will be converted into the measure gn tilde of f to the power p. That's what I'm saying. So the measure m1 here will be equal to gnf tilde, where measure on the codomain will be just this measure. It requires some checking these identities with this particular choice of a function, but that's true. And if you apply this now identities between the Lebesgue integral, you will realize that this integral will change into this integral. Now, if you further couple this with this integration by parts consideration, you also will have this identity. The reason I pay so much attention to these connections between the Lebesgue integral functions and distribution functions, and this particular integral too, which is because this approach to Lebesgue integrable functions, or the functions which are integrable with some power p, this approach via distribution functions proved very effective in many equations in mathematics.